that we're going to be looking at is how dissolving something in water that already contains ions might affect the ability of a compound to dissolve. So we're only going to look at the very narrow point of view of having a common ion, which is specifically there is one of the ions present is also one of the ions present in the substance you're trying to dissolve. So the initial concentration of one of the ionized ions is not zero. So we went ahead and filled in this first table. So if you are dealing with water and you want to dissolve lead 2 chloride in water, then there wouldn't be lead and there wouldn't be chloride. But this is not pure water. This is water with salt in it. And so in this compound is completely ionized, which means if you did a chart for it, all 0.5 sodium chloride becomes 0.5 sodium and 0.5 chloride because it's completely dissolved. So that's why you put 0.5 there. So the only difference would be this initial row, you would have one of the ions already present. It would still be X amount dissolves, creating X and 2X, but at equilibrium, you'd have X and then 0.5 plus 2X. Okay. So if we look up the solubility constant, okay, the expression KSP, lead ions, and chloride squared. Because please remember that in the brackets is the formula, not the coefficients. That's not 2 chloride, is chloride. So whatever the formula is, that's the concentration of that. Okay, so this is the solubility constant expression. The KSP, you find it in Appendix J. So what is the solubility constant? Was it one of the ones we did last week, or is this a new one? I think we've already done. It's 1.6 times 10 to the negative 5. Okay. So I want to point out something mathematical for you. These two numbers, when you multiply them, after you square that one, you multiply them together, you're going to get this number. So in order to get this small number, are these going to be big numbers or small numbers? They're going to be small. In order to get a small number like this, these values have to be small. Because when you multiply them, after you square one of them, you get a really tiny answer. And so they have to be small. If they were big, you'd get a big number as an answer. So because of that, and because this is related to how much change occurs, the change is going to be really small. X is going to be really small. So that's the mathematical part of this. So if we plug in X and 0.5 plus 2X squared, okay, we've got a polynomial going on right here. Because this is the concentration of fluoride at equilibrium. If you do the math here, you're going to get an X squared term. And then what are you going to do with this? You're going to distribute that into here, which will give you an X. You'll have a number. You'll have an X squared, and X cubed. Okay. The math is just going to go beyond, and it's going to keep going. But we know that the value of X is going to be dependent on this number here. And the reason that the math is going to go crazy is because of this thing right here, this number plus the change. So there is a math simplification that we are going to do for the things about the behavior of things in water. This only applies to the behavior of things in water. So our math simplification, when your constant is to the -4th or smaller, and -5 is smaller than -4. Okay, so it's not -3 is bigger. So if your constant is -1, -2, -3, you cannot do what I'm getting ready to say. It has to be small. The smaller it is, the smaller X is. So it has to be a really small constant so that you get a really small X. If that is -4 or smaller, then if you have a polynomial like this, where you have an amount plus a change or an amount minus a change, not an X here, but if you have an initial amount plus or minus a change, you can mathematically cancel the change to simplify the math. I didn't cancel it up here. This is just a math simplification. Okay. So if your constant is -4 or smaller, you can ignore the X that is either plus or minus an initial amount. So you cannot ignore the plus X when you go from 0, because going from having none to having some is an enormous change. But we are going to go from 0.5 and we're going to add a teeny, teeny, tiny, tiny amount that we're probably going to end up rounding because of significant figures. The X is going to be so small versus the 0.5. So mathematically, you can ignore this. So that will simplify it to X times 0.5 squared is equal to this right here. Okay, so once it's simplified, then we will get 1.6 times 10 to the -5 equals X times 0.5 squared. And then you're just going to solve for X. X is still the solubility. X is still the change. So I got 6.4 times 10 to the negative 5. And that's my X. And for solubility, X is the solubility because it is the amount of the solid that can dissolve. And so once you get X, you just tack on molarity and then your formula. If you take this number and you plug it back in, it would go wherever X is in your chart. X is not eliminated. It's just mathematically will not affect your final answer. And so if you plug this back in, if you did that times 2 and added it to 0.5, and then you rounded it to 2 significant figures, it's still going to be 0.5. Okay, so look at number 2, and I want you to do the solubility in water and then the solubility in calcium fluoride. So you've got to write the dissociation and then set up the chart for it dissolving in water. And then the same situation, but it's going to be dissolved in 1 molar calcium chloride instead of just pure water. If you've forgotten what to do, look back at your notes on the ionization, and all the charts look the same for solubility.